Welcome to another CAN seminar series presentation here. There's some UI checkers now. Yeah, it's just okay. Well, again, it's my pleasure to introduce this week's CAN seminar speaker, Professor Hadi Vidani. Actually, Hadi is one of our new faculty members, and he's in our transportation group. He's an our systems group, and he's been actually with us for a year almost, I believe, right? Semester, but he came a little early, maybe last year. Semester started. Anyway.
I was here for the recruiting weekend, but on and off. It started in July.
Well, Hadi is actually on the system side, but actually his background is more general than that. Transportation is some of I guess topics he's been working on, especially in civil engineering. He has a PhD program anyway, in civil engineering, University of Southern California, where he obtained in 2012. But he had an electrical engineering master's degree also from USC as well. So doctoral research focused on the uncertainty classification for complex physical systems, specific application of model reduction, Markov chain model, precision processes. Now, some of you may be familiar with Professor Oyang's but what he did, he's going to talk about a similar topic actually. Uncertainty quantification using expansion. It has been applied to, as he was telling me, some of the payment management, maintenance planning schemes at Berkeley.
Yeah, absolutely.
So he'll get to introduce that to us and learn techniques and how we can apply that.
Thank you very much. Thank you very much, everyone, and thank you all for here to the seminar. I will treat this seminar as an overview. So I consider you students who are interested in learning more about uncertainty construction tools, in particular the polynomial chaos expansion is a technique to model the uncertainties, the random variables, and to be able to make a stochastic analysis and design using this polynomial chaos technique. So this is more of an overview. So I would like to everyone, if you have any questions, please do stop me, and want to have this more interactive than a one-way presentation. So uncertainty quantification became relevant because we wanted to depend more on computational models in addition to theory and experimentation. So I would like to first make the case for why computer models are becoming more and more relevant to the engineer of future cities and communities. So if you consider this to be a city, we have at the center of a city consumers and citizens that live in that city. So we want to serve the people live in it. So they have different needs. So we need to provide for them water, electricity, transportation should be available for them. So we have different people in different disciplines are trying to design and optimize these systems, infrastructure systems that provide these utilities for consumers. And overall, if you look at the city as a combination of interdependent infrastructures that we have, and quantify the coupling that they have between each other, you need to have very sophisticated modeling tools because individual theory that is developed at different disciplines will not be able to describe the overall interconnected systems, behaviors of that, and let alone how to design and optimize those systems. So scientific inquiry, which used to be dependent heavily on theory and experimentation, nowadays is becoming more and more dependent on computation, right? So computation can also think of it as a computer experiment. So
if you compare it
with an actual experiment where you create a prototype of your actual system and you test it and you observe the behavior of that prototype and extrapolate it to an actual system, there are cases where this is really impossible or very difficult to do. There are cases where these systems, these prototypes are very expensive to actually produce. So, for example, in a city, we want to, for example, consider a certain scenario and see what's going to happen. Given that scenario, you can't really run that experiment at that large scale. It's very expensive and impractical. There are experiments that are harmful. So, for example, if you want to study the disease progression in a community, you can't possibly go ahead and use certain virus in the community and see how, what's the progression rate for that community. So this is not something feasible. And then when especially you want to consider different scenarios, so you want to design a system that is robust under different environment scenarios. So you need to repeat this experiment multiple times under different scenarios. So given the expense that is associated with creating this prototype or these actual experiments and the harms that it can cause to the actual citizens. So these are certain situations where computer experiment is the only way to go. Now there is a big problem with using these computer models, and that is computer models. We typically don't rely too much on them, right? We don't know how much confidence should we have in these computer models. Theory, is 100% guaranteed to work, right? And experiments is the closest thing to the reality. Right? We are observing the reality. There are cases where there is difficulty in extrapolating the result of a test to the real world situation, but they are relatively well accepted in the scientific community. Computer models, on the other hand, has been always dealt with a little bit of caution, right? Because we don't know what are the errors associated with these computer models, what kind of uncertainties are involved, and so on and so forth. And these kind of questions really dates back to early 1960s, where there was a nuclear test ban negotiated at the Congress that would have stopped all the nuclear weapon tests. So this could have meant that there was not going to be any progress in terms of the nuclear program in the U.S. And the reason is that by then, computer models, the researchers in the labs did use computer models to design these devices. But these computer models were verified and validated heavily with actual experiments, and that was no longer going to be an option. So they started to think about, okay, what are we going to do with these computer models? We haven't really thought about how much confidence do we have in these computational models from a computational standpoint. We always tested them with an experiment and said, oh, okay, this is good enough. This is good enough within this range, right? So they started to think about how can we continue having these complicated computational models that can describe very complex systems, like a device that consists of multiple different components. How can we use computer models and draw some confidence intervals around the predictions from this computer models? So an initiative started, which was the Accelerated Strategic Computing Initiative, and the objective was to evaluate or increase the predictive capability with validated physics-based simulation tools. Right? So that is when all this, computational science and engineering area or terminologies started. So we have now validation and verification as a very well and established area. So that was the origin of this efforts for computational modeling and quantifying the confidence in the computational models. Now let us talk about the uncertainty that we have in these computational models. Because that's what we care for, right? We want to see how much error or how much discrepancy between the model prediction and actual system. So let me use this very loose definition of uncertainty, which is basically the distance between our model predictions and the real system outcome. So if you take D to be an outcome in a real world, f of x to be the result of our simulation, this E term is basically what includes the discrepancy. Right? What denotes the discrepancy between. And there are multiple sources for this discrepancy and error in our computational model. First of all, our system could have inherent variability itself. So even if we have the most perfect models, the system itself could be inherently uncertain. But let us say that we have a relatively deterministic system, something that can be described with a little bit of modeling efforts, but the model may not be enough to represent that. So there might be aspects of that model that is not captured in the derivation of conservation laws, first principle models, and so on. So there is model discrepancy. That is what is known as model discrepancy. And then when you establish this model, there are parameters in this model. So for example, if you have a traffic flow, there are parameters in the traffic flow that you want to calibrate based on the data. But the data could be noisy. There could be missing information. You could not have the luxury to observe every individual cars, or at the level that you are building your traffic model, you may not have even any access to a meaningful experiment or observation. So there is data incompleteness or noise also that contributes to this E term. Right? Another potential source of error is this discretization that happens when you basically discretize a partial differential equation into a finite difference model, a finite element model, and so on. So that is a potential source of error. So we have all different possibilities combined and compressed into the single term. But if you want to be really rigorous, you need to distinguish between all these four potential sources of transfer. Now there are different ways to treat these uncertainties or errors. One is probability theory. The other one is possibility theory, which is an extension of the fuzzy set and fuzzy logic. And the other one is an evidence theory, which is kind of like an overarching theory over possibility theory and probability theory. We in particular focus on probability theory. This approach by Noel Kells that I will talk about is mainly based on probability theory. So in the probability theory, we have a set of components. You need to fix a sample space where you draw your samples from. So if you have a random variable, you could take values between 0 and 1. So that 0 and 1 range is a sample space. The sigma algebra is the set of all possible outcomes from that system, right? So if you have, for example, two-dimensional system, then any two-dimensional space will be a potential outcome of the system. And then there is a measure, a probability measure on this sigma algebra, which tells you what is the probability of that outcome. So for example, if there is an outcome of value between 0.5, then you can attribute a probability measure to that. You can say there is 20% probability that this value is between 0 and 0.5. And usually we're dealing with probability distribution function, probability density function. So this is our sample space, and this could be a probability density function that describes that these values are more likely than the values that are here. Okay? So that's just the probability theory. So what is uncertainty quantification? So uncertainty quantification is a field now. So there are conferences. There is a SIAM conference on UQ. There are international conference on uncertainty quantification. So this is becoming an independent field where the researchers work on advancing the tools to quantify the uncertainty. So the mainstream uncertainty quantification tools are based on probability theory. There are methods that are based on possibility theory, but they are not mainstream. So what I'm talking about here is the mainstream. And it is approximation theory driven, meaning that it is based on interpolation, projection, finite elements, these ideas. So instead of having a Monte Carlo sampling, fully Monte Carlo sampling approach, try to use interpolation to accelerate the stochastic computation. And it's a computational character. So this is typically used for cases where you want to numerically solve something rather than deriving an analytical solution for your equation. Also, the current hot areas are, just for your reference, it's a high-dimensional problem. So we have tested many of these techniques on small problems. We are at the place to push the boundaries and to consider problems with 200 random variables, 150, 500 random variables, and this is the state of the art. So the adaptive techniques where you just, there is a mesh involved with this technique, so we want to adaptively change the mesh based on your problem. There is increasing interest in addressing the model discrepancy, that component that I talked to you about. And then consider another very hot area is the construction of past surrogates or approximate models for the reality. So these are some of the UQ tasks that people, I mean, you can categorize different papers based on this category. One is uncertainty representation, where you have a random input to your model, and you want to say what is the probability distribution for that random. So, for example, the travel demand to your traffic flow problem or system. You don't know what the probability is for that traffic demand. So you want to use some survey data, some information from observation, and you want to
model the uncertainty or the probability distribution for that random. Now, once you have that random input and you have your model, you want to see what is the probability in the prediction of your model. So, for example, what are the delays, the overall delays in the network, right? So this is typically system level, a core scale quantity of input that we have. So that is what we call uncertainty propagation. So you have a model that is a stochastic, you have random inputs. You want to see what is the outcome of your model given the uncertainty. Now this is a forward problem. You're going from input to output. Now there are inverse problems also of interest. One is the calibration, for example, where you make your prediction and then you observe your system at perhaps at different scale or at the same scale, and then based on this comparison, you go back and update your random input, okay, or the parameters of your model or the random. The other one is the design of experiments. Sometimes you get some observations that are not very informative. So you run another set of experiments, your parameters, the probability model for your parameters doesn't change at all. So you want to get new, meaningful, or more informative observation, so that there is a reduction in the uncertainty in your parameters. And then there is verification and validation, which basically means that you have this model, you're using this model, you want to see if it's a good model. So you run the simulation, you test it against the experiment, and that tells you whether or not your model is valid. And this is basically a higher level question. So this is a very basic question, and these are the questions. And then if you go one level even further, the accreditation and the certification. So these are the things that policymakers are interested in, right? So this talk I will give you an example and talk about the uncertainty representation, uncertainty propagation, and also the model calibration. So the example that I will show is an example on the calibration and the ranking of different models that you have for systems. So if you could have a traffic problem, and then there are different models at different granularity. So for example, there is an agent-based model, there is a gas flow model, there are different types. So there is a low fidelity gas flow model, so you could have different candidate models for your system. You want to see which one is better, and by what margin. So you want to say, for example, model 1 is twice as good as model 2, right, in terms of some metrics. So that's the objective of model ranking of different models. So the example that I will show you is the coarse graining of molecular systems. This is just basically a paper that we are working on, and that's why I'm using this example, because I have the results readily available, and it's relatively simple to follow. So You have molecular systems. You have a set of atoms and molecules, and then you could have a model for these systems at different levels. So you can perhaps ignore certain atoms. For example, for the water model, you can ignore the hydrogen atoms and still get a very good description of the behavior of water. So that's actually a true argument. So we want to see if we reduce certain aspects of this model, how much fidelity are we losing from that model? So these kind of questions we want to see if we can answer. So the objective is first to calibrate these models. So there are parameters involved with these models. We want to see what the right value for those parameters are with the observation. So for that, we use surrogates to reduce the computation time. And I'll tell you why we need to do this reduction. And then the other objective is to make ensemble predictions. So we want to, based on this relative fidelity that they have or plausibility that they have, we want to use all three models in order to make a prediction, not individual models, right? So how do we combine the predictions of individual models and make an ensemble prediction? So first, I'll start with the calibration. So here's how a deterministic calibration works. You have a model, then there are parameters involved with that model. Right? And you know that the parameters have a set of, to take different values, right? So you start with a range for this variable, and you want to find the best parameter value that explains in the best way the observation, the observed quantity. So this is a range for your parameter values. You go to the response surface of that quantity. For example, we are observing the density of water, for example. Okay. And you know that the density of water is right somewhere here, and then you have some response surfaces, and at the intersection of those response surfaces, you find the value that explains best this observed quantity, and that is your calibrated parameter, the calibrated value for the parameter. So the red one is the optimized parameter value for a set of calibration data. So this is deterministic. We start with a fixed observation, water density, fixed value for the parameter. Now, the other way to do this is the stochastic calibration. So we are still doing the same thing in principle. It's an inverse problem. You have a set of observation. You want to see what is the value or what you want to calibrate. You want to estimate your parameter. But we do this in a probabilistic sense. We consider a range for the parameter values, and we want to find the optimal probability distribution for them instead of the optimal value. So we start, for example, with a uniform distribution over this parameter, and we want to go through this response surface and comparison with the observation, and then arrive at a posterior distribution. This is what we call as the optimal distribution or the posterior distribution when you use the data to do this parameter. Right? So again, deterministic calibration, one fixed value for the parameter. Stochastic calibration, you have a probability distribution. So in general, we could have multiple values with different probabilities. You can still make a point estimate. You can say, for example, the best value is the one corresponding to this peak value. You could in principle do that. But what is being done here is really a combination of parameter uncertainty and observation uncertainty. Right? So our data is noisy. So this is, for example, the density of water. We know that there isn't like a 1%, 2% noise with that experiment. So that's the noise in the observation, and then there is an uncertainty about the parameters that we have. Right? So we added two uncertain components to our inverse problem already. So let us talk about this polynomial chaos expansion and see how it works. So if you consider a forward problem where you have an input uncertainty, and this is a black box, this is your simulation. So this is like a travel demand, and this is the traffic simulation. So Monte Carlo simulation is the conventional approach that people use in order to do this uncertainty computation, where what you do is to draw a sample from your input, for example, a travel demand, a realization of the travel demand. You run this deterministic simulation, and you get a quantity of interest, for example, the throughput in your network. So that's one realization of the output. And you repeat that for multiple samples of your input, and then you have multiple samples of your output, and then you can fit a probability distribution to that. Okay? So this is what we call Monte Carlo simulation. Now, polynomial chaos approach is, in principle, a different approach. So we have a different representation for random variables. We no longer deal with sampling from the distribution, from probability distribution. We represent the random variables as a vector in a orthogonal basis, like a Cartesian vector, Cartesian coordinate system. So this is our input, and input is a vector in that system, and output is another vector in that system, right? So each random variable is a vector in this Cartesian coordinate system. So if you change this vector, you would get different probability distribution. So this is an alternative representation, alternative model for random variables. So this is similar to the idea of Fourier transform. So when you have a signal here, you do the Fourier transform, and then it's a combination of a set of orthogonal sine or cosine functions, right? So this, the composition of this is a combination of this orthogonal basis functions. So we're doing the same thing for the stochastic case. So if this is a random variable, our random variable is a combination of orthogonal random variables. Right? So we have these coefficients of the expansion, and this is the sine or cosine basis function. So in this case, we're using polynomial functions, but in analogy with the Fourier transform, we have a set of orthogonal basis functions and the coefficients. So that's the idea. So you can think of it as a vector space representation, right? Because this and this is orthogonal. So what this allows us, this orthogonal structure, what it allows us is that we have an analytical expression that relates the outcome to the input, output to the input, right? Whereas in this case, it's a probability density function. You can't really say, for example, this value here, I mean, if you don't draw samples, you can't say this value here is related to which value on the input. Whereas in this case, you can make that correspondence because these are based on some inputs C. So these are functions. So it's an analytical function representation for the output in terms of the input. So you have that structure, rich structure that allows you to do fast calculation and inverse policy. So this is what we mean by orthogonal basis function is basically this, that the inner product of Ci and Cj is 1 if I and j equals each other, and is 0 if they're different, like a sine and cosine function. So as I said, it allows us to do fast post-processing. So once you get these coefficients here, then the average or the mean of this outcome is just the first coefficient. The standard deviation is just the summation of a squared coefficient. And the sensitivity indices, these are Sobol sensitivity indices, is just, again, a closed form expression of these coefficients. You don't need to draw any samples afterwards. So this is readily available. Okay. So that's the advantage that we have. So how do these orthogonal basis functions look like, right? In the case of Fourier transform, we have sine and cosine function. In this case, for example, if you use uniform distribution, so if C, which is this value here, is uniform distribution, then they're Legendre polynomials. This is the first, the zeroth term. This is the first term. This is the second term. This is the third term, and so on and so forth. So this guy and this guy is orthogonal. This guy and this guy is orthogonal. Right? All of them are pairwise orthogonal. And then for different random variables, there are different polynomials that are orthogonal. So for example, if you use Gaussian distribution, there's Hermite polynomial. Any questions so far? So let us see. So you can think of this as surrogates, right? I mean, this polynomial chaos or this Fourier transform as a surrogate that you can use instead of your actual computational model. Okay, here's how we compute it. So this is a coarse-grained model for water. We have this oxygen atoms. Here, one oxygen atom. These are all oxygen atoms. We just ignore the hydrogen. And then this is a potential for the way that these oxygen atoms interact. So if it's parameterized by the distance between them, so R sub ij is the pairwise distance between each pair of atoms. Right? So this is potential. You need to run the simulation in order to for example, calculate the density of water, the enthalpy of vaporization, the structural properties, and so on and so forth. So you run simulation. So each point here is a simulation. So this is a value. Each point here is a value of sigma, a value for lambda, which is here, and a value for epsilon, which is here. So these are the three random variables that we consider to be random. Right? So if you consider a grid of points here in the parameter space, then basically that would give you a set of prediction for your quantities of interest, and then you can consider a response surface on that. If you, for example, interpolate between these points or do the projection between these points. Right, so back to the deterministic calibration, this response surface is used instead of the actual simulation. So for the actual simulation, for each value of parameter, you would have to run this molecular dynamics code to give you the density, for example. Whereas in this case, you would just go to this response surface, approximate or surrogate response surface, and read that value. You don't need to run your model. This is just an analytical expression for the density. And the same thing for the stochastic calibration. Right? So this was an overview on, I mean, the idea, the main idea, the core idea behind polynomial chaos representation. Now let us talk about the model calibration again from another, I mean, using this other figure. So for model calibration, you have your model. The input is P, the output is Y. You want to compare it with data and find the best value, right? So you start with different values of P. You run the simulation. You get the corresponding Y values, and you choose the one that is closest to your data. Right? So this is the closest one to the data, and you go back to find out, okay, this corresponded to this value. So that is your deterministic parameter. In the stochastic calibration, you start with a prior distribution, you run the simulation, you draw samples from it, and then you compare it with noisy data, and you change this, I mean, just loosely speaking, you play with this probability distribution, you change it, and then find the optimal one that gives you a probability distribution for Y that is closer to the observation. So that's the idea behind the stochastic calibration. So the theorem that we use for Bayesian inference or stochastic calibration is the Bayes rule, which on the left-hand side we have the conditional probability, or the probability of parameter given data is proportionally related to the probability of data given a parameter times the probability of that parameter when there is no data. So this is a prior distribution. When see what's going on here. So prior is our prior knowledge about that parameter. Posterior is the updated knowledge about that parameter. And that's when you use the data. So If you start with the posterior distribution, you run simulation, you get output, model output, you compare it with data. And then you start with this prior distribution, you get an updated distribution, which is your posterior distribution. So it involves the simulation. Now, how do we run this? How do we find this posterior distribution numerically? We do a sample-based algorithm, which is called Markov chain Monte Carlo simulation. So it really is based on the comparison between a sample that is drawn from the prior with the noisy data. So at each step, we draw a sample, we run the simulation, we compare it with the data, and if it's a good sample, we keep it and draw another sample, run the simulation, get the output, compare it with the data, run another sample. So we repeat this many times so that we have a large number of samples here, and then we can fit a probability distribution. So that is where we get the posterior sample. Now the problem is that these simulations could be very expensive, right? So for each value of parameter, you have to run, for example, a traffic flow for a very large network. So you can potentially do that, especially if this MCMC algorithm involves 1 million steps, 1 million iterations. So 1 million iterations, each one involving a costly simulation. So this is impossible. So the remedy to this is to replace the simulation by something fast. That's what we call the surrogate. So instead of running the simulation, we want to have a mathematical expression, an analytical expression that can give us the final answer at no cost or at a very small cost. So here is how we describe the surrogate. So the exact response surface is one that you draw samples from your prior, you run the simulation, you get your Y. So if this is your parameters, this is the model output, this is the exact response surface, one that is actually populated based on simulation, a full simulation. But this is very costly. This is what is very costly. So we want to use a surrogate. So eventually a surrogate, I'll go with to the last row. A surrogate is a very low cost model, if you wish, which is analytical, where you can get samples from your parameters and just feed to this mathematical expression and find the corresponding approximate model output, which is hopefully the same as your actual values here. Right? So this is, to some extent, similar to this. Right? This isn't surrogate that we use. So how do we construct this surrogate? We construct it based on the polynomial chaos expansion, like a Fourier type expansion. So we draw a very small number of samples and run the simulation only at those samples, and then find this surrogate. And then use that surrogate for the other large number of MCMC samples. So the idea, the computational saving really boils down to these three facts. So this is, assume that you want to run your, let's go to this. You want to run your MCMC sample for 1 million times. So N, big N is 1 million times. C is the computation cost, the simulation cost for the full system. So this is, let's say this is 2 days. So 1 million times 2 days, unbelievable. Then you consider the cost of surrogate-based MCMC, where you only use, instead of 1 million samples, 200 samples with the same cost, 2 days, but you use the lower cost. This is in terms of 1 second, right? The order of 1 second or 2 seconds. So this is the cost of surrogate evaluation times the big N, which is 1 million, right? So the MCMC simulation, surrogate-based MCMC simulation, has two terms that are both small compared to this guy. Because in this first term, we have a much fewer number of samples compared to the MCMC simulation. Here we have the second term, we have a much faster calculation, or low cost calculation. So this would be the calibration where you use the approximate, compare it with the data. All right? So just the result of this of the application of this method to ranking different coarse grain models. So let us consider 3 different water models. One is TIP4P, where you have the long-range interaction between the atoms. So this is very costly. This takes more than around 2 days to simulate. Right? To get the density of water and other bulk properties, you need to run this. This will take on a parallel supercomputer. This is 2 days. This is typically this is a relatively faster model. This will take 12 hours. And this is a very, very fast in the order of 1 or 2 hours, this LJG model. Right? So when we go down, we have lower fidelity. So people have approximated these models that can run faster but have lower fidelity. So can we compare them in terms of their predictive capability? So I talked about the ensemble prediction and model averaging, which means that if you have multiple models, how do you use both models? For example, if you have 2 models, how do you use both models in order to make ensemble predictions about it? So this is just a history about the Bayesian model averaging. It started with research in economics, where they combined predictions from different forecasting models, because especially in these fields, like climate modeling, there are different models with very, big differences, but they can't really pick one over the other. So they need to use all their candidate models in order to make ensemble predictions. So the idea is that you have a quantity of interest that you want to predict, the throughput, for example, in your network. You have a set of observation at different locations. You have the traffic counts, you have the traffic flow, and then you have an ensemble of models. You have 1, 2, 3 models. You want to calibrate these models and make predictions based on all 3 models. So this is how you combine them. So this is the weights that you consider for each model prediction. This is the individual model prediction, and this is the ensemble prediction. So we combine them based on these weights. How do we calculate these weights? This is called posterior model probability. It's basically like a posterior parameter probability. This is a posterior model probability, which involves this equation, and the first term here is the marginal likelihood of model M. So how likely is it that model M predicts observation D? Okay, and this is the prior probability of model. So even before running any experiment, any calibration, we know, for example, model 1 is more accurate than model 2. So for example, you assign 70% probability to model 1 and 30% probability to model 2. So this is how it works. So in order to rank different models, you use Bayes factors, which is the ratio between different marginal likelihoods. So the marginal likelihood of model K over model J is called Bayes factor, and the model likelihood is given by this integral. And then posterior odds, if you want to also incorporate the prior model probabilities, what I just described, you would get this ratio, and we call this posterior odds. Now, for that problem that we saw, there were 3 different water models, TIP4P, MW, and LJG. So we can compare them based on different observables. So you can say, for example, in predicting density, TIP4P is better than MW by a factor of 2.28. In, for example, predicting the structural property, this is RDF, radial distribution function, TIP4P is 3 times better than MW. So now we have a quantitative measure of how good they actually perform compared to each other. The ensemble prediction, so for example, we have the MW model and LJG model. So this is the error in reproducing some data. So this is 0.97, this is 0.95. So if you have higher value, it means that it's erroneous. So there's a larger error value. So this is the value of individual models, and then if you combine them and make that prediction, you'll get a smaller error. So it's possible that the ensemble prediction is better than individual prediction. So that is really the key. So you could have models, individual model 1 could capture certain aspects of your physics, and model 2 could capture certain other aspects. So if you combine the two, the overall prediction could be better. So yeah, so that is just an example of how we use this data. At the end, if you use all this machinery, these algorithms, what it boils down to is just a set of numbers that can tell you how much confidence you should have in different models. So with that, I thank you for your attention, and we'd be happy to take any questions. Yes. Sure. Where does it fail to? Well, they are competing approaches.
And they represent same model, so
right.
You can use Monte Carlo or this method.
Or this method.
But Monte Carlo requires a lot of
samples.
So I was looking at some studies that they were comparing the results.
Right.
Okay, this one is better or accurate.
Right. So,
but there were some examples that they were failing to present Monte Carlo.
Right. So in which cases would a Monte Carlo simulation perform better than polynomial chaos? Yeah. So in one case where Monte Carlo is still better is high dimensional problems. So if you have a very large dimension, you can't get much from this polynomial chaos approach yet. So this is what is being done to try to get that accuracy that you get from Monte Carlo simulation. So that's one area. The other areas is when you have non-smooth behavior. So this is basically polynomial chaos with all these polynomials that you had, these response surfaces that you had, they were smooth, right? I mean, if you have a smoothness, then with a set of, with a good number of basis function, you could represent very well that response surface. But if your response surface has discontinuities, then you can't really do much with this functional representation. Whereas on the other case, Monte Carlo, which is a sample-based, it's a point-wise technique, can capture that because it's so each point could be on this side of the discontinuity or on the other side of the continuity. But these polynomial functions are typically global functions, so they would have hard time capturing that discontinuity. Yes.
At the very beginning, Professor Fukumoto, you were talking about there's some application of in the maintenance.
Yes.
So I was wondering if you could elaborate a little bit more.
Right. So one application. So one of the application is the pavement management. One of the techniques to do the pavement planning, maintenance planning, is the Markov decision processes. I'm not sure how familiar you are with that. So Markov decision processes, you can think of it as an optimization problem, which tells you for each distress type at different state what kind of action you should have. So for example, if you see a crack, for example, of this size on the pavement, should you repair it or should you just leave it and repair it the next year? So this is a question that a pavement management system answer. So to answer that question, you need to have a dynamics. You need to have a dynamics model of the way these damages progress through time. Right? So you want to say, for example, if the pavement is in damage state 1, next year it's going to be in the damage state 2 or damage state 3 with a given probability, right? So people use Markov chains to describe this dynamics, right? So you have a damaged pavement, and a Markov chain and transition probabilities that tells you if you are at state 3, the chance that you will be in a worse case next year is 20%, for example. And the chance that you be the same damage state is 80%. So this is what Markov chain does. So you have this dynamics, and then on top of that, you wrap an optimizer around that to tell you, okay, there is a cost associated with the repair, and there is a cost associated with this damage. So you have a combination of two costs. And over a time horizon, you fix a time horizon, say for the next 10 years, or for the rest of the service life of the pavement. I want to minimize the overall cost, given this probabilistic dynamics that I have. So what should be the best policy for this? The best policy tells you that for each damage state do a certain action. So that was actually a description about this Markov discrete process. What we did was to represent that dynamics, add another layer of uncertainty to that dynamics. So consider a probability model for that transition matrix and use a polynomial approximation for that matrix, which facilitate that optimization problem. Because that optimization problem is very difficult to solve if there are additional uncertainties involved. But if you have this polynomial approximation, this functional representation, you can very easily solve that optimization problem at a much lower cost. So that was the motivation, and that was a contribution by that work. Yes.
I have a question about polynomial chaos when you had orthogonal integrators. So yeah, this one, yes.
This or
then yeah, this one. So my question is about if there is hidden assumption for the black box. It seems that it is necessary to have this assumption that your black box should preserve orthogonality in output.
Well, so let me tell you how we solve this first. Maybe it can answer that question. So one way to solve this problem is to, as I said, so we have, these are our input uncertainties, and these are the same input uncertainties. So one way, so this is the same basis representation. So one way to solve this is based on the Galerkin projection. Okay, so the Galerkin projection is that it tells you that you run the simulation and the distance between your solution, right, your solution compared to, well, the residual in that solution projected on each orthogonal basis function should be minimized. So it's like a finite element technique where the solution compared to the approximated solution, that residual term is minimized. The projection on different components is minimized. The other way to do this is non-intrusive, where you draw a sample here, and then you run the simulation through your black box. This is just the same black box. This is just a deterministic simulator. And get one sample of U, all right? And then draw another sample of C, find another sample of U, and then interpolate, for example, between those samples, or do the Galerkin projection. So if you do this, then you have a black box that could be anything. That could be any simulator.
The black box could be anything. For example, a very simple function, or not function. It is function C. A map like
right.
f of x is equal to 1, right? So basically, if you doesn't preserve orthogonality for the output, you know what I mean? So
yeah, we preserve it by using the same basis function.
Okay.
So this is how it's done. So you have a set of basis functions that describes your input. You use the same basis function to describe your output. So this is an assumption. We impose, yeah. So we impose this. So we say that it's like a conjecture that the output should live in the same space, described by the same polynomial function, and then that preserves the structure of the output. So you have the freedom of finding the coefficients. No, right? Because you have fixed the structure here. If you fix that structure, and the coefficients can be, you can play with the coefficients, then you have the orthogonality. Yeah, good question.
Need to have a meet and greet session, potentially diving into what his research focuses or general questions that you guys might have that we could benefit from him. Just a direct interaction with the student. From students